One of the things we've learned here at the Marshall Space Flight Center through the history of all the vehicles that we've developed here, from the Saturn vehicles to the Space Shuttle and now the Ares vehicles, is that doing development work at full scale is crucial to making sure that we meet our mission objectives. My name is Robert Carter. This is the Weld Process Development Facility at the NASA Marshall Space Flight Center. I'm the lead engineer here in this facility, overseeing the assembly of Ares 1 upper stage. What we do is build full-scale hardware. If you do something small scale, if you do it half scale, 1/6 scale, you can miss manufacturing problems that will arise when you go to a full scale.
My name is Sandeep Shah, and I'm the subsystem manager for manufacturing and assembly for the upper stage rocket. If you imagine the height of the upper stage rocket, it is made up of several subsections called barrel. The barrel itself is made up of 6 barrel panels, and we weld the 6 panels together and make up one complete barrel. 14 foot tall and 18 foot in diameter. For space exploration, we're always looking for material that are lightweight and strong.
On the Ares 1 upper stage, removing a pound of mass from the vehicle actually gives us an extra pound that we can put into orbit. On a car, you can add a pound or 2 here or there, and it's not really going to influence your gas mileage to any great extent. You add a pound or 2 onto the side of a launch vehicle, and it has huge implications on how much cargo you can put into outer space.
So we compare one material with another material based on their strength to weight ratio. The material of choice for the upper stage is an aluminum lithium alloy called 2195.
My name is Okaro Leslie, and I'm a contract specialist here at Marshall in the Office of Procurement. What I do is I buy goods and services from contractors, local contractors across the globe. I procured some aluminum lithium plates, 2195. Our technical colleagues come to us with requirements. They expect us to go out and find who can provide the good or service. We have to do market research. I had to go and find out about aluminum lithium plates, some possible vendors who can make the plates. We have to make sure that our colleagues here at Marshall are getting what they need.
Aluminum lithium alloys are known for their high strength and low density, which means that they have a very high strength to weight ratio.
There's other ways that we use to reduce weight on the vehicle. You see the panel behind me, you see the grid pattern in that panel. If you look at this panel edge on, you see that this material has been reduced in thickness down to less than 1/8 of an inch. The original material thickness was about 1.5 inches. So what we've done is taken a sheet of material and removed a bunch of excess mass out of the material. The interesting thing is that by engineering this panel properly, we can achieve similar strengths as we could have if this was a continuous solid chunk of material. Only in this case, we've removed about 95% of the weight.
So you have the basic material strength, but then you also have this grid structure, this design-based stiffness, so that your barrel panel doesn't flex during flight.
After we have removed all this material and done our engineering homework, we end up with a component that is nearly as strong as it would have been had we not removed any of this material, and yet we've saved 95% roughly of the weight of the panel, and that's a lot of extra cargo that we can put into orbit.
Just like any manufacturing process, welding is a process that has evolved
A lot of people have visions of welding being sparks flying and a guy with a helmet. What we do here at Marshall is not like that at all.
Most welding processes require a lot of electricity and a lot of heat. The idea is you want to get a metal as hot as you can and then fuse the metal together. So you get this high energy arc that heats up and vaporizes a little bit of the metal. The process heats up the metal and it fuses it together. But in that process, what happens is air gets trapped inside of the metal itself. So that oxygen gets in there and causes the weld itself to actually degrade and not be as strong as you want it to be, because you always want your weld to be just as strong as the material around it.
So the welding we do here at Marshall and at NASA in general these days is a process called friction stir welding. The way the friction stir welding process works is we use a rotating tool called a pin tool, and as the tool is rotating, that material is compressed under high loads, greater than 10,000 pounds of force. As that pin tool travels along, it plasticizes a zone of material. And when I say plasticize, that means that it gets hot enough that it softens. It becomes sort of like taffy.
At the molecular level, what happens is that the joint disappears and there is no more a seam. So the molecules from one side of the joint have been mixed together with the molecules of the other side of the joint to make one piece of material.
These two panels were originally separate pieces of material, and this pin tool was rotated at several hundred RPMs, traveled along at several inches a minute, and then was retracted. And so what you see is a completed friction stir weld. This hasn't been machined or polished or anything like that. This is actually what the weld looks like when we take it out of the machine. If you look at the back side, it's completely flat where it was pushed up against the welding anvil. This is about as good as it gets. For all intents and purposes, from a structural standpoint, the two pieces of material have become uniformly bonded together.
This is not the first time friction stir welding has been used in spacecraft. The advancement that we are making in upper stage is to incorporate almost 100% friction stir welding.
A lot of what we do is solve problems related to issues that come up as we're doing the development work. People like to point out reports that come out that point to an issue that we found on the vehicle that we're working. That is actually the natural part of development work. It's a good thing when we identify issues associated with a vehicle during the development phase so that we can find a solution to those problems before that flight hardware is sitting on the pad, or worse yet, before that flight hardware is in space. The Ares vehicles are more than just experimental, one-time use vehicles. The Ares vehicles, not just the Ares 1, but also the Ares 5, are really the key to making the future of the American space program possible. These are the vehicles that are going to enable us to get into outer space and enable us to launch heavy cargoes to supply space stations and to put man onto the moon and onto Mars.
This is a job where you see your work launching humans into space. I mean, that has to be one of the satisfying jobs.
I get the enjoyment of knowing that this facility is the cornerstone right now of the Ares project. The road to Ares goes through this shop, and so knowing that it's a real joy.